Hi everyone, welcome to week 6 of our management science course. So I've got a couple of updates for you and reminders. New is a discussion thread, the third of 5. It is a question related to shortest route algorithms. I asked you to do some investigation of some things online. It's due no later than midnight on Monday the 17th of July. And it is worth 2% of your course grade. I hope you're enjoying doing these post investigations. I prepare them for the purpose of helping you understand how the concepts we're exploring in this course apply to the real world. So this is another one that I think you'll really appreciate with regard to Google Maps and so on, and understanding the origins of the algorithms behind it. Okay, also, reminder for your team project planning. Again, in Canvas under week 4 module, there is a link to student pairings. I encourage you to reach out, at least make contact with your assigned teammate. If you've got any questions or problems for this, please let me know. It's going to be due in second week of August when you're going to have to prepare your material and submit it. And so let's begin to finish Chapter 6. Chapter 6 will be the source for all Test 4 content. Test 4 is going to open on Monday, July 10th. I'll talk about that at the end here. And we need to explore 4 additional types of distribution and network models from Chapter 6. Last week, we spent time exploring the transportation problem. This week, we'll do assignments, transshipments, shortest route, and maximal flow problems. Okay, so the first one this week, let's talk about assignment problems. And our goal with an assignment problem is to generally to minimize total cost. Generally, there are exceptions. I'll talk about that in a few minutes. It's the total cost of assigning a certain number of workers. We're going to assign that variable to be M. They can be agents. There's different terms that could apply to some number of jobs, and we're going to call that N. Given the cost of that worker for performing a job is variable C, and we use the subscript ij, meaning the worker I, the job J. So the cost of worker I completing job J, we'll identify that. We assume for the purposes of our work that all workers are assigned to one and only one job at a time. You probably well know in the real world, life's not always like that. And there are tool solutions that will allow you to get around that variable. But for the time being, for what we're going to do at our basic simplistic level, we'll have this assumption. Now, I do want to point out an assignment problem is pretty close to transportation problems. And as a result, we can solve this as a linear programming. Now, on the next slide, I do have a network representation. You're not going to have to draw this network for this online class. But if we had something with 3 workers and 3 jobs on the next slide, let's go through that. This is what it would look like. Remember, agents or workers, M, on the left side, tasks or jobs to be done on the right side. In this case, N. And then the cost is reflected here in each case. And remember, the cost of C subscript 1 means the cost of worker agent 1 performing the task. In this case, it's also a 1. And then, of course, there are unique costs associated with each of these. So if I were to ask you a question, how many total assignment alternatives are possible? It's represented by the number of arcs. Now, if all assignments are possible, every worker could conceivably be assigned to any task, the answer to that question about how many are possible is M, quantity of M, times N, the quantity of N, as in Nancy. So if there are 3 workers and 3 jobs, the answer to that question would be 9. But what if one assignment wasn't allowed? Say worker 1 could not be assigned to job 3 for some reason. How many alternative assignment alternatives would there be? And that would simply be M times N, which is 9, minus 1. Or if there were 2 that were not allowed, we would have m times n minus 2. So I wanted you to understand that concept, okay? All right, I always try and point out how things work in the real world. Let me point out to you an example of how Uber, a well-known transportation company, uses this type of assignment algorithm as the foundation for how they make assignments for rides to riders as riders request. So in their case, going back to our agents, these are their drivers and their vehicles, and the tasks, these are the customers to be picked up. So they use this type of work, and you can follow this link yourself and read the article. They use this to optimize their distribution and assignment of resources of their people and their vehicles. They can do it based on distance, time, so on and so forth. They can vary what the determination for what they're attempting to optimize is. This concept also works for search and rescue operations. It's used by the U.S. Coast Guard. It's used in military applications by the Navy and Army for assigning weapons on certain targets in terms of optimizing that as well. So it can apply to a variety of different circumstances. Now, there are some special cases. In some cases, an assignment problem, if the alternatives are being evaluated in terms of revenue or profit, attempting to maximize them rather than cost, where we're attempting to minimize, we can turn it around and solve it as a max problem. And again, I already told you that when an assignment is unacceptable or cannot be made, we don't have a decision variable there. We don't have an arc that can be used. Okay, so let's go through an example of something from our text, the pages 263 to 266, foul marketing research. Okay, let me take a step back on that page assignment. My apologies. It actually begins on page 274 and goes up to as far as 278. Okay, nonetheless, let's talk about that. So in terms of some background, if we look at the bottom of page 274, table 6.5, you're told that here is a series of potential project assignment personnel, project leaders. They're identified in order, three of them, Terry, Carl, and McClymans. And for each of those three persons, they're potentially assigned to clients 1, 2, and 3. And there are durations given for how long it would take that given person, given their experience, to work with that client and solve their needs. And those are given in units of days. So I want to point out to you something. You've got to make sure you're dealing in the same units when you're setting up these problems. You have to work in days, hours, weeks, months, years, whatever it is that you're working from. Make sure you're working in common units. So in this case, I'm going to pull up a file that's out on Canvas, and this is the way the problem is given to you. Now, I have filled in these cells. I'm going to highlight them right now in yellow. I have filled them in for you with this particular template. And in some cases, perhaps for the test, I might not fill those in, but rather would give you some information, maybe in a table, just like you see on page 274 in the text, and you would have to fill that in. But these are the same data that are included with that particular example. So once we identify that data, this is a model that's set up just like all the others I give you. So we can go to the Data tab, load Solver, do a quick sanity check. This is indeed set up for a min, simplex LP. Let's run Solver, see what this tells us. And this tells us that the minimum time, in this case, to complete this work, based on these assignments, is a total of 26 days. And how would that go? Let's see. So McClymans would be assigned to client 1. Terry would be assigned to client 2. Carl would be assigned to client 3. And they, in turn, in terms of their durations, color these cells, would be 6 days, 15 days, and 5 days. That's how we arrived at 26. 6 plus 15 is 21, plus 5 is 26, except that Solver did the solution for us quickly and automatically and gave us an optimal solution in terms of the shortest time to get this solved for those clients and their client needs. It would work like that in terms of these persons being assigned here. Therefore, the total minimum time would be given as 26. You're going to have to work and solve that kind of problem in test number 4. So be ready for that. Okay, so let's go back and we're going to address the next topic. We're going to talk about transshipment problems. And you can refer and follow along in the textbook for transshipment problems starting on page 266 through 272. All right, so transshipment problems, what do they look like? They're similar to transportation problems, but we have intermediate nodes. Let me show you a little visual what that looks like. So we have sources, we have destinations, or supply and demand, but we have intermediate nodes. Think of them as warehouses, things going from point A to point B, seller to an Amazon warehouse to you as a buyer at home. So they go through these transshipment nodes, and typically we're trying to identify how many units should be shipped from each network arc. Okay, each path here should source 1 go to the intermediate node here to get to that destination, or should source 1 go to node 4 to get to that destination at the lowest possible cost, typically the minimum cost. Again, this is an LP problem, and here's an example of what something would look like in this particular case. Now, in this case also, we have cost. We identify the cost of shipping from node 1 to node 3, cost of shipping from node 3 to node 6, so on and so forth. And again, these are supply side, just as we have with transportation. These are given as the demand side. And we identify the supply and the demand. We're going to do that also in Excel. I can show you how to do that. Okay, so let's work through an example of how we would use Excel to solve and optimize the transshipment problem. To optimize, in our case, we're going to work on the presumption of lowest cost. And so if you refer to the text, again, pages 268 through 273, we're given, actually 266 through 273, we're given an example of a company called Ryan Electronics. Now, Ryan Electronics has 2 plants for the origin or the supply nodes. They have 2 warehouses for transshipment or intermediate nodes, and they have 4 possible retail destination or the destination or demand side nodes. So 2 origin, 2 transshipment, 4 destination nodes. Now, we are also given data about their cost of shipping between each of those nodes, and all routes are possible. Every route from between nodes is indeed possible. So let's refer to the template I have out on Canvas. And again, similarly, I'm giving you some of the data here in this particular example, but for a quiz, or pardon me, for a test, for example, I might not fill this in. I might ask you in turn to fill that in. But the template would remain the same, and I would highlight the cells where you have to do that. So in this case, we have these costs, and we merely need to run Solver to identify our optimal solution. Set up for min, it's simplex LP. Let's run. Let's see what we get. In this case, our minimum total cost would be $5,200, and these are our answers for the number of units shipped. And so in terms of where Kansas City would get supplies and so on as an intermediate node, and so on and so forth. So net shipments and supply shipments and so on, all the supply would go out of Denver and Atlanta. The intermediate nodes, Kansas City and Louisville, would not have any left. All right, we're going to stop here and go into the next topic.